Cantilever. Cantilevers. Now, when you talk about cantilever, what are we talking about? We're talking about is a beam whose ends is fixed. One of the end is fixed and one is free. Example, this is a diagram of a cantilever. This shows the fixed end. Then this is the beam. This is the free end because here is no fixed and there is no support anyway. So now this is an example of a cantilever. So now in calculation of a cantilever, to find the shear force, finding the shear force and bending moment. When we are doing this, we start from the free end. We're starting from this free end. All cantilevers, if you want to calculate it, you start from the free end. I'm not saying you start from the right. If this cantilever was to be like this, this is the fixed end now. Now you start from the left. So you must start your calculation from the free end. Sorry. You must start your calculation from the free end. So now let's take a question. Let's say a cantilever beam of length 2 meters carries 3-point loads as shown. I will draw the diagram. So now draw the shear force and bending moment diagram. So now this is the cantilever. So now the total distance is what? 2 of the cantilever. So it carries what? 3-point load. So this is 1-point load here. We have it as 0.3 kilonewton. There's another point load here, 0.5 kilonewton. Then one at the end, we have it as 0.8 kilonewton. So, and they actually have distance apart. So from here to here, this is 0.5 meters. That's the distance. Then from here downward, we have 0.7 meters. Then downward, we have 0.8 meters. So now I like naming them. So you name here A, B, C, D. So now you start with your shear force calculation, but before you even calculate, you can actually draw your shear force diagram. By looking at this, you can just picture out what your shear force diagram looks like. Now this is it. Now there is a point node there, so this will go up, it will move to C. There's another point node at C, so here will move up to move to B. There's another point node at B, here will go up, it's move to A. So this is how your shear force diagram is supposed to look like. So anything you're calculating, if you cannot get this thing, just know you are wrong. Now let's start the calculation. So let's go shear force calculation. Shear force calculation. Now, like I said earlier, we're going to be starting from the free end. So this is the free end. So we'll start our calculation from here. So this is how we'll do it. We'll start like this. Portion CD. CD from the ending. So CD. Can I DC anyhow? So now f of x is equal to 0.8 kilonewton, which is constant. Now you are looking at only CD. Now you close your eye as if you are not seeing this C. It's as if you are cutting this beam from this edge. So it's like you're not seeing this C part of it. You're only seeing the D. That is why it's only 0.8. So that is how we're doing it. So now if you go to portion BC, f of x will now be 0.8 plus 0.5. Now why are you adding it? You are adding it because now you are in BC, and now it's not as if you are cutting the beam from this B part. So now what can you see? You can see 2-point node, which is C, and D, that is 0.5 and 0.8. So you add the two of them together. So that is 0.5 plus 0.8, that is equal to 1.3 kilonewton. So now portion AB, we have that f of x is now equal to what? 0.8 plus 0.5 plus 0.3. That is equal to what? 1.6 kilonewton. Why did I add 0.3? Because now we're cutting this beam from A, so I can see the 3-point node. So add up everything, as I got 1.6. So with this, we are done with the shear force calculation. So now we'll go to the bending moment calculation. So now bending moment. Calculation. Now the bending moment calculation is always trickier, because now you need to generate formulas to solve it. Portion CD. So now we have bending moment. So now when you are talking about moment, you are doing force times distance. So that is why you are generating the formula, force times distance. So you have mx instead of f of x. So this f is just basically the force. So this one ms, you are talking about the moment. So now portion CD, mx is equal to, let me take it here back, this is CD. So now you're generating a formula, because like I said, you block this place as if you're not seeing it again. So you are only seeing this 0.8. So we'll actually write 0.8 x, because now this is the force, this is not the distance. You are assuming you don't know the distance. So this 0.8 you're seeing here, you are assuming you're not seeing it also. So you are assuming you don't know the distance. So that's why you use the word x. So now x is power 1. Once you have something like this, it's just like a linear, because it's just like basically a straight line. If it's x is power 2, it's a parabola. So that's what we're saying here. So now you will now solve bending moment of D, because this is portion CD. So you do D and C. Bending moment of D. Let's go. So now this is D. This is point D. So now we already know that this is 0.8, but D has not moved any distance. There is nothing at the front of D, so it has not moved any distance. So it's actually 0.8 times 0, something like this. 0.8 times 0. Why? Because D, this D, it has not moved any distance. So now that is equal to 0 kilonewton meter. So now, bending moment at C, 0.8 times what is the distance moved by C? Now this is point C, it has moved a distance of what? 0.8 meter. So now their x now will now be 0.8 also. 0.8, that is now equal to 0.64 kilonewton meter. Make sure you put your unit always. So let's go. Portion BC, we have that mx just know this formula that you had before, repeat it again. It's like an easier version of getting your formula. Repeat that formula again. That is 0.88. Then you now add plus. So now we're looking at portion BC. So now you're cutting it at this point. So we have 0.5 also. So now plus 0.5. Now the distance of B to C we already know is 0.7. Yeah, but now you look at, since you are trying to generate a formula, you look at it like that, like this. The distance of B to D straight is actually what? 1.5, because 0.7 plus 0.3, that is 1.5. So now, since you know that the distance from B to D is 1.5 and the distance of B to C is actually 0.7, so your formula that you're generating will now be x minus this 0.8, because your total distance is now 1.5 and you want to get this 0.7 back. In order for you to get this 0.7, you subtract the total distance minus one number that can give you this distance back. So now the total distance from B to D is what? 1.5. So now you subtract 1.5 points from this 0.8 in order for you to get this 0.7 back. So this is what I'm trying to say. You just put in bracket x minus 0.8. So now this is also linear. So we go. So bending moment. Now if you check bending moment of C again, you see that you still give us the same answer. So now we have 0.8. What is this x of C again? So your x is now 0.8 again, because of C is obviously from C to D, that is 0.8. So now 0.8 plus 0.5. Your C is still C now, so 0.8 minus 0.8. So 0.8 minus 0.8 is actually 0. 0 times 0.5 is 0. So this times this is still 0.64. So now that is to tell you that this formula is actually correct. So now I actually want to do bending moment of B. So now I have 0.8. Your x now is now what? What do you think your x is? So now this is B. The total distance of B to D is what? 1.5. So your x is actually 1.5 now. 1.5 plus 0.5 into bracket 1.5 minus 0.8. Now if you put this in your calculator, you have 1.55 kilonewton meter. So now that's how to do it. So now the last one, you will say portion AB mx is not equal to what? Write down the last formula down. 0.8 x plus 0.5 x minus 0.8 plus, now you can see this point on B, so that is 0.3 plus 0.3 into bracket. So the total distance now is 2. 2 minus what will give me 0.5. That is 2 minus 1.5. So that is what? X minus 1.5. And it is still linear. So now insert. If I do bending moment of B, it still gives me the same, so there is no point. Bending moment of A at once. So that is what? 0.8 times 2 plus 0.5. 2 minus 0.8 plus 0.3. 2 minus 1.5. So the final answer, bending moment of A is now equal to what? 2.35 kilonewton meter. So now So they asked us to draw the diagram for them. So let's draw the diagram. If you want to draw the diagram, you start from the question, you draw back this, then say 0.8 kilonewton, 0.5 kilonewton, 0.3 kilonewton, the distance 0.5 meters, 0.7 meters, 0.8 meters. So now the shear force diagram, you have it that draw a straight line. So now shear force diagram, your first one is what? 0.8. 0.8 is at the positive side, there's no minus sign, so it's at the positive. 0.8, 1.3 and 1.6. So you can see 0.8 is lower than 1.3 and it's also lower than 1.6. So 0.8, let's assume here is 0.8. So reach here, this is the D. 1.3 is higher than 0.8, somewhere here. Let's see. We're assuming this is not a graph. I want to read the graph will be more distinct. So now 1.6. So you are done with the shear force. So can you write 0.8, 1.3, 1.6. So now your bending moment diagram, you take, here is what? Your point A, your point B, your point C, and your point D. So now you take another, you must draw them like together. So now you take another line. Let's go. So now your D, when you start solving your bending moment, your D is at point 0. So this is your point 0. So this is your point 0 here. So this is 0 kilonewton meter. Then your point C is at 0.64. So now 0.64. This is a linear, take it down like this. So this is your point C, 0.64 kilonewton meter. Then your point B, 1.55. so it's still linear, just take it down the more. 1.55 kilonewton meter. Then your A is 2.35. So just actually very easy. 2.35 kilonewton meter. So this is easy. I was so simple like that. So now you can try other questions. And see how they will work. So let's try this question. Number 2. Kilonewton, 5 kilonewton, 3 kilonewton, 2 kilonewton. So we have A, B, C, D, E. So here, and here. So I can say 0.2 meter, 0.1 meter, 0.3 meter and 0.1. So this is another question for us to solve. Find the shear force and bending moment and draw them and do it. Simple. So now let's look at it. We have shear force calculation. That's how we start. Shear force calculation. Now, like I said, we'll start from the field. So the last portion is of DE. So we'll start portion DE. F of x is equal to what? 7 kilonewton. Why is it just 7? Because you are cutting it before the D. You are assuming you are cutting it before the D. You are cutting the beam before the D. So now you can see only the 7 kilonewton. You cannot see this 5. So you write on, you pick only this 7 and you say it is a constant. So now since f of x is 7, then you go portion CD. Your f of x is now equal to what? 7 plus 5 kilonewton. That is equal to what? 12 kilonewton. Why is it 7 plus 5? Because now portion CD, you are cutting it before this C. Now you can see 2 point node. These are called point nodes. So you can see 2 point node, which is what? 5 and 7. So you add up the two of them together. That's how you get this one. So now next one is portion BC. Your f of x is now equal to 7 plus 5 plus 3 kilonewton, which is equal to 15 kilonewton. Now we already know that we're cutting it at this point, so we're adding up them up. So now portion AB, your f of x is now equal to 7 plus 5 plus 3 plus 2 kilonewton. That is equal to what? 17 kilonewton. So like this, you are done with your shear force calculation. Very simple, just be adding them, just very simple thing. So we go into our bending moment. Bending moment calculation. Now our bending moment calculation. So you already know that we're trying to generate formulas. So let's start on the first one. Portion DE. Now bending moment. So we're using M, like I said last time, M of x. Now what is the first thing? 7. So now portion DE. We are not saying this part, we are saying the 7. So we have 7. You are generating a formula that is the force times your distance. So that is why it's 7x. 7x because it's the force times the distance from D to E. So now this is what? Linear. You must indicate it there. So now the bending moment at E is now equal to 7 times 0 y, because this is at E. It has not moved any distance. There's no distance, so it's just like at a point. So that's why it's 0. That is equal to 0 kilonewton meter. Then your bending moment at D, 7 times 0.2. So now, how is it 0.2? You can see that from D, it has moved a distance of 0.2. So that's why we do 7 times this distance move. And that is 1.4 kilonewton meter. So now you go to the next portion. That is, let's say, portion CD. Now your M of x is now equal to, so we look at it. Portion CD. Like I'm cutting it here. So we write the previous formula, which is 7x which is 7x plus, so now you're looking at it, this is CD. Now the distance between C and D is what, 0.1, but the full distance between C and E is what, 0.3. So now, in order for you to get this 0.1, you must generate a formula. What will subtract what that will give you 0.1? So now you can say the full distance minus this side will give you this side. So the full distance, we're taking it as x minus 0.2. So now that's what, plus 5. Because why is it 5? Because this is now, this is a point node and that's 5 kilonewton. So plus 5 into bracket x minus 0.2. So that's how you take a formula. So now bending moment at C, 7 times 0.3 plus 5, 0.3 minus 0.2. That is 0.3. From C to E, 0.1 plus 0.2, that's 0.3. So that is 0.3. Now, first a calculator, this will give you 2.6 kilonewton meter. Go to the next portion. Portion BC. M of x. This is also linear. So now M of x is equal to 7x plus 5x minus 0.2, then plus, this is BC. So now the distance from B to C is 0.3, but the total distance is what, 0.6. So now what will you subtract from 0.6 that will give you 0.3? Also 0.3. So that's how you get a formula. So now, and this point node that you can see now is 3. So that's what we use, plus 3 into bracket x minus 0.3. So now the bending moment of B, why is it, I want to use 6 now as x, but why? Because it's 0.3, 0.1, 0.2, add up, that is 0.6. So let's do 7 into bracket 0.6 plus 5 into bracket 0.6 minus 0.2 plus 3 into bracket 0.6 minus 0.3. That will give us 7.1 kilonewton. So now, question AB, I have M of x is equal to 7x. This is also linear, plus 5x minus 0.2 plus 3x minus 0.3, then plus, you look at it again, AB, now you can see 2, and I want to get 0.1, so that's just like saying x minus 0.6. I thought I'd be explaining it. So that's 2, 0.6. So now we have B, bending moment of A, 7, 0.7 plus 5, 0.7 minus 0.2 plus 3, 0.7 minus 0.3 plus 2, 0.7 minus 0.6. That will give us 8.8 kilonewton. So now drawing it, we know, I will repeat this drawing first. Question. It's 7 kilonewton. Five kilonewton. 3 kilonewton. 2 kilonewton. 0.25 0.1 meter, 0.3 meter, 0.1 meter. So now doing the shear first. Put a line. I've explained all this, right? So after I put the line, so now your shear force, the first one we have is 7, so you'll go up 20. Display this in the last one. The next one is 12. So 12 is higher than 7. 15. And 17. The straight line, sorry. These are A, your B, your C, your D, your A. So now for the bending moment, the first one is 0 kilonewton meter. To come down to 1.4 kilonewton meter. Since it's linear, it's just a straight line. So to come down to 2.6 kilonewton meter, come down to 7.1, come down to 8.6. So we're done with that function. So virtually we are done with this type of question of cantilever. So now I can just give you to solve. You can do this. This is another cantilever question. I'll just give you, try it on your own. So this is 6 kilonewton, here is 5 kilonewton, here is 4 kilonewton, here is A, B, C and D. So here is 6 meter, here is 2 meter, here is 2 meter. So you can just solve this by yourself. So now in my next video I'll be talking about uniformly distributed load. Let me just do a brief explanation of this uniformly distributed load. I can have a table. Let's just say this is a table. Now, someone can come and stand in the middle of this table. So now, I can be standing in the middle of this table, making this a point node, or I can lie down on it. So now, this is what we have. If I'm lying down on it, that means I'm spreading my weight in like the sides of the table. So I'm spreading my weight across this. So now, if I'm to solve this, I need to find a way to make it to make my weight stay in this middle point. So now that's what we'll be doing in uniformly distributed load. So it's going to be quite different from all this we just did now, but it's still the same step. So you just need to learn some things down. Like we'll make use of wx squared over x over 2, over 2, ws squared over 2, because now since we are trying to find the middle point, this also not because w is the weight of like the person that is sitting on the beam, then the x is the distance, then over 2. So this is how we're going to find the middle point. Thank you for watching.